So after you, okay. Okay, so we can start, right?
Yes.
Okay, so maybe we just start. So today we are very happy to welcome back another Rutgers PhD, Liang. So he actually he's not just a math department student. He was actually a physics student at Rutgers, and so he knows both mathematics and physics. So today he will talk about the mathematical theory of gapless boundaries of 2+1 dimensional topological orders. So please.
Oh, thank you very much. Thank you for inviting me to come back to give a talk in Rutgers. It's always a pleasure. So I haven't seen a lot of the friends for a long time. At first I thought it's a math seminar. I should give a math talk, but Ija told me that he want to hear more about the recent work we had with a physicist. But after some consideration, I feel like my recent work, most of them are too physical in the sense that it's really difficult to give a math talk about those things. So I decided to give this one. It's a mixture of mathematics and physics. In particular, I think it's a good chance to show one of the Ija's fundamental results on the vertex subalgebra, rational vertex subalgebra, which gives module tensor category what come out of those results, and what kind of application it will it occurs almost 15 years after that. Okay, so my talk will be how to say that? It will be a mixture of physics and mathematics. So it won't be very easy to for a mathematician to understand, but I'll try. Okay. So let me, even though the topic is quite is a physical topic, but I will start from mathematical problems. A well-known problem in mathematics, so is for a given module tensor category, find a mathematical structure D such that its dream field center gives C. Okay, this problem is crucial to the problem of extending 2+1D rest into REF TQFT defined by a module tensor category down to a point. So this question has been asked, I think, by Restik in the middle of 90s. How to extend the Restik into REF TQFT down to a point? What to assign to a point? So for these problems, let me give a mathematical remark. So if you start with module tensor category D, then its dream field center is essentially a double. Okay, when I highlight it, can you see it in the blue color? Okay, so if you start from module tensor category, you get take the center, you get double. So essentially it looks like a square. So in some sense, by trying, so we're trying to make sense of taking the square root of a module tensor category. Okay, so finding a solution of finding solution of that equation is amounts to taking square root. I want to remind you that in history, there are a lot of famous problem involving finding a square root. The first one is square root of -1. Another is a square root of Laplacian operator. And we know what the answer is. That's a Dirac operator. Okay, but now we want to take the square root of a module tensor category. So we have
just one question. This D tensor D bar, is this look like the chiral and anti-chiral part?
Yeah.
Okay.
The D bar is you flip the braiding. You choose the anti-braiding of D. Yeah. So a partial result is
when you say mathematical structure, you mean a category with some nice
bucket? It had to be some category, right? Because after you square it, you get some category. But
you're talking about the dream field center. Okay, all right, fine.
Yeah, but when I give the partial results, you will see what's going on. So when C is the dream field center of a spherical fusion category M, then we know that this TQFT can be extended to a point, which is to each of which we assign the D. The D is nothing but That's a mistake. Sorry, that's not D. That's a typo. The D should be M. Sorry, M is a fusion category, a spherical fusion category, and such a TQFT is called the Fourier-Viro TQFT. So there are solutions. So, but this solution does not solve all the problems. So some multi-density category have such kind of solutions. What kind of multi-density category? They're twin field center of fusion category. But most of the multi-density category does not have such solutions. Okay. Okay. Well, there are some partial results by Fried Hopkins and Lurie and Telemann in 2009, but that one I don't even know the precise result. But they get a twin field center of some infinite type of category, and but the twin field center only contain a factor, which is a multi-density category. We have something else, so they didn't solve the problem completely. There's some other result in 2007. Andre Henrik, he proposed the following results. The twin field center of the category of positive energy representations of a base loop group, base loop group, is equivalent to the category of positive energy representation of the free loop group. Okay, because the positive energy representation of the free loop group also give you a multi-density category. Okay, that's a partial result. Around the same year, we proposed something different. Okay, but that something different is more general. So, but you can see that from generic multi-density category, there is no clue from mathematical side how to take a square root. Well, there's no clue. You know, it's got to be some categorical result, but categorical structure, but you don't know what it is. Okay, but it turned out that there are clues from physics. In physics, topological order are certain quantum phases defined at 0 temperature, whose low energy effective field theory are topological field theories. So let's not worry about how the physical definition are, physical notions are, but just try to imagine there are some kind of physical materials. Okay, at 0 temperature, they have quantum field theory, effective quantum field theory description, which is given by topological field theory. Okay, these are called topological orders. In particular, we know that 2D, this 2D is a spatial dimension. I'm using the convention of the condensed matter. Yeah, when I use a small d, that's a spatial dimension. Okay, so this 2D is spatial dimension, or 2 plus 1d if you want it for space-time dimension. 2D topological order is described by a pair. The C is a unitary multi-density category. Okay, the object. Oh, sorry, that's another typo. Sorry, the object in C. Sorry, so many typo. The object in C are topological excitations, or also called anyons. Okay, and the morphism are observable on the word line. They are sometimes called instantons. So morphism in the category are called instantons. But anyway, this is not important. The important thing is that the multi-density category catch the fusion and property and the breeding property of the anyons. So the anion usually can be breeded. That's why the category also breeded. So multi-density category have a breeding. Okay, so they catch all the fusion and breeding property of the anyons. Another C is a real number called the chiral central charge. It's not so important in our talk, this small c. Okay, but the only thing important is the multi-density category. Okay, why it have anything to do with us? Okay, it turned out that when the chiral central charge is 0, this topological order can have, or not always, can have a gapped boundary. Let's forget about the detail. What was a gap boundary? But it turned out that when the boundary is gapped, this gap boundary can be described by a unitary fusion category. Why is that? Because on this gapped boundary, you can also have something like anyons, but it shouldn't be called anion anymore because everything is located on the 1D space dimension, right? 1D space dimension, you cannot do any breeding. You can only do fusion of particles. So in that case, all the particles living on the gapped boundary form a fusion category without breeding. Okay, without breeding. So so the gap boundary can be described by unitary fusion category. Again, the object in the category are so-called topological excitations or age excitations or boundary excitations. Morphism are again instantons. Okay.
So this is basically like the boundary conformal field theory or something.
No, it's not it's a boundary topological field theory.
I see. Okay.
It's not conformal. Yeah. the gapless one will be conformal. I'll jump to that. I'll talk about that. Yeah. So, but in this case, there is an interesting boundary bulk relations. It turned out that the boundary fusion category are deeply related to the bulk module density category. Not only that, the boundary determine the bulk. So what happened is that the boundary is a fusion category. The bulk is a module density category. The relation is that you take the dream field center of the boundary, you get the bulk. You get the interior, which is called bulk in physics. So in this picture, you have a 2D. Just imagine this blue things are 2D material. It has a 1D boundary. Okay, but in this picture, I show you that it can have different boundaries. So it can have a different fusion category living on different, defined on the different boundaries. Okay, they share the same bulk because a different diffusion category can have a different, can have the same dream field center.
So
and it turned out that
is this the same thing as you see in our paper? We have this meromorphic center of the open string. Is it?
That's a slightly different center. Yeah,
okay.
The meromorphic center is also a center, but this center closer to something I'm going to talk about. Yeah, I'm going to talk about later. In conformal field theory, what kind of center it's corresponding to. Okay, but here is dream field center. It's just dream field center. Okay, so in particular, you can prove the following result: two H are share the same bulk or share the same dream field center, even only if they're Morita equivalent. Okay, so different boundary are Morita equivalent. The purple domain wall are essentially invertible bimodules, but that's not a focus of my talk. But it just shows you some feature of that, and this kind of things will pop up later. Okay, all right. Why it have anything to do with us? Okay, but the things is in this picture. Well, if the boundary is a fusion category, the bulk have to be dream field center of a fusion category. But these kind of a module density category are very, very, very few. You know, most of module density category cannot realize in this case. Okay, so without knowing what a gapless boundary is, okay, the year is totally wrong. I think it's 2015, sorry. In 2015, we provide a physical proof of a boundary bulk relation for topological order in all dimensions. We have a informal argument showing that no matter how you define topological order mathematically, we don't know how to define it, but there is a powerful physical argument to show you that the bulk is the center of the boundary have to be true in a very general sense. Okay, what does this mean? This means that if you give a module tensor category C, which is a very generic module tensor category, in that case, you won't have a gapped boundary anymore. In general, you will have a gapless boundary. That gapless boundary is described by conformal field theory. But you know, since this is well known in early 90s by the work of Wheaton and by the work of Xiaogang Wen, but after that, nobody really know what is precisely mathematical description of the gapless boundary. The only thing we know is that it's related to conformal field theory. Okay, but now this theorem tell you that whatever the gapless boundary should be, it should have a mathematical description such that its dream field center is a generic module tensor category. So that's a great hint for us. So we're looking, remember that we're looking for solution of this kind of equation. But now we don't know where to find a solution. But the physics tell you that if you know how to describe the D of a gapless boundary, you find a solution. Okay, so that's why what I'm saying here is that the Mother Nature provides a solution to the equation. If you understand how to describe the gapless boundary of 2D topological order.
Excuse me, Liang.
Okay.
There's a question.
Yes.
There's a question in the chat box from Ishan. Is it that the different boundary theories live on different parts of the boundary?
Yeah. Yes, it's very possible, and they can separate it by a domain wall between them.
Uh-huh.
Yeah.
Do you have some other way of saying why there are different boundary theories? I didn't quite understand myself.
Why there are different boundary series? Well, we're mathematicians, right? We don't need a physical result. Let me just say, it's simply because for the same C, you can have a different square root. The square root is not unique, just as, yeah, that's a mathematical answer to this. All right. Okay, so now let us read the mother book's nature's book, right? But the book is too big. We need to know where to look at, right? So since the category C, the multi-tensor category, describe the fusion and braiding property of anions, and which can be viewed as observable in the 2D phase. Of course, in the long wavelength limit, but that's a physical term. Let's forget it. But then this question mark in this equation, because C is observable, so the question mark have to be the observable on the chiral or non-chiral gapless. Well, I shouldn't use age. I changed different. I changed from a different slide. The age in physics usually mean boundary, because in this case, the boundary is one dimension for condensed matter. So space dimension is one. So they usually call the age. Okay, that's why my title.
So when you say gapped or gapless, you mean these like the spectrum is discrete
spectrum.
and
Yeah.
right? Okay.
Yeah, continuous in the thermodynamic limit. But that's a physical way to say that it's a conformal fusor in some sense. Yeah. All right, so, but we know that for generic topological order, which is given by a generic multi-tensor category, they should have a gapless boundary. Okay, they always have boundaries, because you have a material, you just cut it by half, and the nature will provide a boundary for you, either gap or gapless. If it is gapped, then the bulk have to be the dream field center of a fusion category. If it is gapless, well, by the theorem, it have to be the dream field center of something, describe the gapless boundary. Okay, so let's look at what's on the gapless boundary. So let's just carefully analyze what's on the boundary. So observable on the boundary, now I change to space-time, it become a 1 plus 1D. The space dimension is 1. Okay, now the other one is time. So this picture, I draw a space-time worksheet of the boundary. So now become a cylinder. And we know that this is known for a long time. So on the edge of the 2D bulk topological phases, on the edge, that means on the boundary of that, okay, there are gapless, the chiral age mode. These are something known to Witten and to Xiaogang Wen and in the early 90s. Okay, I will just take it for granted. For a gapless one, you always get chiral age mode, which should be some state in should be the state in the chiral algebra, which is called the VOA. Physics is called chiral algebra. I will denote the VOA U. So that means the chiral field, the field in the VOA live on the entire 1 plus 1D worksheet of the 1D boundary. Physicists already know this. Okay, there are some kind of VOA on the boundary. They know this. Okay, so it's not new. But what is new is that if we only have this picture, then we failed, because we know that it's impossible to make sense how could this VOA, the center of the VOA, be a multi-tensor category. It doesn't make any sense. There's two different mathematical subjects. Okay, so there's something else. Okay, there's something else on the boundary. So what happened is that imagine that you have an anion in the bulk, you move onto the boundary. What gonna happen? Okay, something gonna happen. Okay, it creates a topological defect. It creates something sometimes called excitation. But anyway, it's called you can call it the topological, some kind of defect on the boundary. You move the particle to the boundary, create a defect. Then as a consequence, the word line support on this defect. The chiral field on the word line support on X are potentially different from U. Remember, the U is the all the chiral algebra leave on the entire worksheet. Okay, but this word line can have a chiral field which is potentially different from U. Because of that, I will just denote the space of this chiral field by AX. I didn't make any assumption yet. Okay, potentially it could be different, right? And this A should relate to this, whatever the defect is called. I will just call that X. Okay. And these turn out that these chiral field also have OPE. You can have a chiral field have OPE along this line, blue line. And this is called the open string VOA, which is a notion which was introduced by EJ and I more than 15 years ago. Okay. It turned out that this open string VOA is also a boundary CFT, as we will see at the end of my talk. Okay. It's an open string VOA. But what is open string? I won't record it, but I would just want to give a comment. It is a non-commutative version of VOA. Okay. So you don't have, you lost the locality. There's no locality anymore. Okay. All right. One more remark is that if X is trivial, so imagine that there's nothing. When X is trivial, just means there's no defect there. Just like an ordinary line here. Okay. So A1 should be U. Okay. So last remark is that. So the one should be viewed as trivial topological age excitation. Just mean nothing there. Okay, so the word line support on it should be U. Okay. Okay. What else? Do you have more? Yes, you can do more. So it's possible that the topological excitation can change from X to Y on the word line, but by selecting a different time slice. Remember this vertical direction is time slice. Okay, time direction. So at a different time, you can insert another defect at a different time, then change the boundary condition to AY. Okay, then it created domain wall. It created domain wall between AX and AY. Okay, that domain wall is called MXY. If someone familiar with the boundary CFT, actually remember I made a comment that AX is a boundary CFT. Why is that? Because if you squeeze this picture, look at the picture. Okay, if you squeeze picture to a line which is parallel to this dotted line from A to X. You squeeze the cylinder to a line, to a plane parallel to this dotted line from A to X. What do you got? You got a 1+1D worksheet, and this blue line is the boundary of that. On that worksheet, you get a 1+1D CFT, and this blue line is exactly the boundary of that CFT. Okay, so that's why. So AX, AY are boundary CFTs, and MXY are usually called the boundary condition changing operator. They consist of all kinds of boundary condition changing operator between two different CFTs. Okay, but once we introduce this terminology, it become a unification of notations, because you can see immediately that let's forget about the first one. Let's just focus on this one. Then AX is exactly MXX. Because MXXX is exactly a boundary condition preserving operators, essentially preserving the. That's nothing but the field, chiral field in the boundary CFT. Okay. So in a sense, the MXY summarize all the data. Okay, let's look at it. What's going on, and we have a more general OPE. We can have a MYZ and MXY, they can fuse to do an OPE, okay, to give a map to MXZ. When you fuse this two, okay, when you fuse this two, you got a boundary changing operator from AX to AZ, so that's MXZ, okay, and clearly this OPE also have associativity, just like the OPE in VOA. As a special case. Yes.
So is it possible to understand this just like using tensor category? Is that the bulk theory if the bulk theory is nice, then see we have a tensor category, and then these boundary thing are actually some algebra, but might not be commutative algebra.
Yeah, exactly. That's exactly gonna happen.
You can still have tensor product because they live in the large.
Exactly. So in the later slides, I'm gonna show you that these OP are intertwining operators of vertex operator algebra. So they become a morphism in the tensor category. Okay, so yeah, I'm gonna show you that. Yeah, well, this special case, special case is not important. We can, I think we have this. Once we have this OP is enough for this slide. All right, so now comes a crucial part. So there is something very important on this blue line. I draw it horizontally now. What happened is that, remember that I said everything in U are live on the entire worksheet, but take a field in U, you can push this, you can do OPE, or you can push the field to the blue line, but in two different ways. You can push it in the one along this path, gamma 1, okay, gamma 1. And you can also push this field along this gamma 2 path. And they all end in the same point on the blue line. But it's not necessary that they are compatible. Okay, so but what are these? You push this field to, that means you do the OPE basically. So each pass give a map from U to AX. Okay, so iota gamma I is a map from U to AX, and this map should preserve OPE, right? So because from physical picture, this map should preserve OPE. So as a consequence, they have to be an open string VOA homomorphism. Every VOA can be automatically viewed as an open string VOA, because open string VOA is just non-committed version of VOA. Automatically include VOA as an example. Okay, there are two, so you get two maps. It turned out that you have to impose a minimal condition in order for this to make sense, just as what we did for boundary CFT. So you have to impose conformal symmetric boundary condition. That's a minimal requirement. It says that, okay, in each VOA, there is a minimal VOA, which is generated by a Virasoro element. Okay, so these sub VOA have to match on the boundary. That means if take V to be the minimal VOA, and this iota map restrict on the V have to be injective and path independent. Okay, that's the minimal requirement. All right, since this is the minimal requirement, so we can impose more general conditions. So in general, you can impose a V-symmetric boundary condition. What is a V? V is just some kind of subalgebra of U, not necessarily entire U. It have to be include the minimal one, must include the minimal one, but not necessarily the entire U. It could be something smaller. Okay, I would just call the V-symmetric boundary conditions. All right, so once we impose this V symmetric boundary condition, what does this mean? This means that this V is transparent on the entire worksheet. Because, right, it's a V fused to AX as embedding injectively, and along different paths the same. So that means the V is entirely transparent on the worksheet. Okay, so what's the consequence of that? The consequence of that is, so the V action must commute with the fusion among all these things. Because you can see the field AX, my axon, MX, but V axon is in a two-dimensional way. In particular, look, this V axon MX in a two-dimensional way, right? You can push the field, do an OPE with the field in MXY. But you can do it in a two-dimensional way. This is precisely how we define a module over VOA. When we define module over V, we require the actions completely local, right? Satisfy the locality. So as a consequence, MXY are V modules. Okay. And moreover, because all these actions, OPE among MXY have to be compatible V actions in a two-dimensional way. So it means the fusion of defect field are determined by a morphism in this category, mod V. So these OP, remember that we have we call this OPE. We call this OPE. It is OPE, but compatible with V. The precise mathematical meaning of compatible with V action is just this OPE give rise to a morphism in mod V. It's intertwining operator because M YZ is a module, M V module, MXY is also V module. This is also a V module. Okay, so this is intertwining operator, respect of VOA V. So this give rise to a morphism in the mod V by Ichi's theorem. Okay, am I going too fast? Any questions?
So you're saying that the morphism. Okay, when you say morphism, but you are okay. I see you basically the view because intertwining operator corresponds to some morphism in the tensor category.
In the tensor category, yeah, by your theorem, yeah.
Right.
Yeah, I should put your name there. Sorry.
Oh no, this is actually the just the I think it's
yeah. Also,
Jim and my work that the intertwining operator corresponds to.
That's right.
Morphism from the tensor product module to another module, right?
Yeah. Exactly.
Okay,
so we obtain a categorical structure immediately. See, the object of this categorical structure is topological excitation on age excitation. Just label, just label XYZs. Okay, that also you can call them a boundary condition of CFTs. And another thing are morphisms, just MXYs, because everything is covered by MXY. Okay, and MXY is an object in the category mod V. Okay, moreover, we have an identity morphism. Is given by this iota along different paths. But remember, when we impose the V-symmetric boundary condition, all this iota map is path independent. So there's a canonical one. Okay, so but I'll use a different notation because in the tensor category, mod V, the tensor unit is nothing but V. Okay, so these are identical, and V is embedded in MXX. Okay. These another data, and another the third data is composition map. Remember, this is just Ham, right? This is the same as a Ham. So the composition of Ham is a morphism in mod V. What does this mean? It's the same axiom as those of ordinary category, except the Ham is an object in another category, and the composition is a morphism in another category. So what does this mean? It means that this categorical structure is a category enriched mod V, or mod V enriched category. Okay. Moreover, it's not only an enriched category. It has when you have two defect on the boundary, the boundary is one-dimensional. You can fuse them. You can see that the fusion is the horizontal fusion. All the word line is fused. If you fuse these two on the same time slice, all the word line support on it also fuse horizontally. Okay, these provide a tensor product in the category. Okay, the horizontal fusion on the one-dimensional space. So it means that this tensor product upgrades this enriched category to a mod V enriched monoidal category. Okay, this notion is very interesting. This notion is essentially introduced only in the same year, just a couple weeks before our paper. Very interesting.
So this enriched tensor category, is it true that every enriched tensor category can become a category in the mod V?
No, no. You have to. But it needs to satisfy certain conditions.
Okay,
yeah.
see
I'm gonna tell you.
Yeah, the main reason I'm asking is in some sense that if you take Moy-Seiberg's polynomial equations, you can actually get a tensor category, but this tensor category is not on the modules for the vertex algebra. So so that basically you can take because Moy-Seiberg is the same simple and with finitely many irreducible objects. So you can take label these irreducible modules by something, and then the each label is an object, and the morphism is defined using these numbers, right? So and then the sort of like you have a tensor category, but it's not on the category of modules. Basically, our tensor product theory really actually give a tensor category on the category of modules. And if you just sort of like this really become a tensor category whose like the fusion rules and so on are the same as what one gets from this just using the polynomial equations, right?
Yeah.
So at least there is one case that one can actually make the enriched tensor category to be a real category on the modules.
Yeah. Yeah, you will see that
general,
this enriched category. This enriched category is actually what people had in mind on what is the chiral CFT is. You will see.
Okay.
It turned out that one more comment is that this is actually a fusion category enriched in a braided fusion category. Because the enrichment, the base category have a higher commutativity. It won't break the monoidal structure. It will preserve the monoidal structure of the category. So this category have monoidal structure, but the base category have to be braided in order to make this happen. Okay. So what's our conclusion? So our conclusion is that all observable on the gapless boundary of 2D topological order can be described by a pair. V is a VOA, which is we call it chiral symmetry because V is transparent on the entire worldsheet. So it's called a symmetry. I will call that chiral symmetry. And everything else is enriched category. Everything else is enriched category. Okay. So in particular, you will see, where is U? For example, U is nothing but M11. So M11 is completely catched by this enriched category data. Everything else is in it, except the data of chiral symmetry. Okay. Now I'm going to talk about the relation between those two. Of course, the relation. Okay, the base category of this enriched category is mod V actually. Yeah. Okay. So let me recall some results of. So now I want to impose some conditions because so far this analysis is completely general. I didn't make any assumption. There's no assumption was made so far. Okay. Now I want to add assumption because we don't know how to do irrational theory, right? So now I assume the chiral symmetry is a rational VOA. All right. If you're a physicist, you probably want to add a unitary, but I won't do that today. Okay, just non-unitary is fine. So for the rational theory, we know that mod V is a modulus tensor category by Ege's famous theorem. Now we in this context, what we know about the conformal field theory? It turned out that the rational conformal field theory satisfying V invariant V symmetric boundary condition can be completely classified for its low genus theory. Well, the high genus theory is conjectural. I put in there. So the high genus theory is not known yet. Okay, but for genus equal 0 and equal 1, you can already obtain following results. Okay, the open part is or boundary theory, sometimes also called a boundary CFT or open CFT, is given by a simple symmetric special symmetric Frobenius algebra. It's a long name. Let's forget about the detail. It's some kind of Frobenius algebra in the tensor category. Okay, and A closed have another fancy name called the Lagrangian algebra. It's some kind of commutative algebra. Let's also forget about the name. Okay, but the point is the closed algebra is the center of the open algebra. This is related to what Ege had asked. This is not a meromorphic center. It says that the center of the open string VOA is the entire closed CFT. This center have a of course, it's precise. When we say it's a center, it's not just giving it a name called center. It indeed satisfies the universal property of center. So it is indeed a center. It's called a full center. But the funny thing is that, well, they live in different category because the closed theory living in the center of the dream field center of the mod B. they're even in different category now, which is normal, right? We know that closed theory is chiral plus anti-chiral, okay? And the open one is the chiral. So they don't live in the same category, okay? But the closed theory is the center of that. Moreover, we also have a result which I guess remind you of the previous one. The two open CFT are Morita equivalent if and only if their center are same. Okay, this is similar to the previous boundary bulk relation I mentioned in the topological order. So CFT have the same property. Okay.
So basically here, what you use are only the tensor category part and the topological field theory part of the rational
Yes.
theory.
Yeah.
So in that case, you are only using the modular functor. Therefore, hygienous theory is there already.
But to construct, but for hygienous theory, you really need a correlation function, because when I said data, I still claim I have OPE. All these defect lines also have OPE. I need that. So then it's a problem.
If you need a correlation functions, then certainly modular functor is not enough.
Yeah, in principle, we want all the correlation functions. So yeah. So I will give an example. For example, a multi-density category given by mod V, then its dream field center is precisely the double. Okay, and let me give you one example. So assuming that you take algebra, which is a trivial one, it's a tensor unit in C. What's its dream field center? It's sorry, not dream field center. It's a full center. Okay, this is called the full center. It turned out this full center is this double. Its box tensor is this center is living in the double C. Okay, so the center is living in a different category, but that's one example. I'll give some other example. Oh, sorry. So some other example. For example, you can also take A to be the internal Helm of XX. What is internal Helm of XX? Is the X tensor X dual. It's also turned out to be some kind of a Frobenius algebra in C. Okay, and the interesting part is that they share the same unit. They share the same center. Their center is the same. So it just means that for the same closed CFT, you can have a lot of compatible open CFT, or the same box CFT can have a lot of different compatible boundary CFT. That's one example. And between each pair of boundary CFT, for example, this one, okay, internal Helm between X and XY, you can define a domain wall between them, which is given by also internal Helm. XY. What's the XY? It's just X tensor Y dual. Okay, or Y tensor X dual. Sorry, it's Y tensor X dual. I didn't write it down, but it's just internal Helm. Okay.
So basically, these are just the Helm, right? So
yeah, it's an internal Helm in the sense that this is also object in object in C.
Right.
All right, so that's one example. I'm gonna using the example to construct a gapless H to you. So a canonical gapless H looks like this. It consists of following data. It's a V together with the enriched category. I will call the C sharp. The H excitation equal to the bulk excitation. They turn out to be the same as the bulk UMTC. Why? This pair represent the bulk topological order. So this C is a modular sensor category describing the anion in the bulk. Okay. Now the H axis in the bulk is exactly the same. Okay. And the U equal to V in this case, and the mod V equal to C. Okay, so the VOA its module category exactly is the bulk module sensor category. Okay, in this case, you can show that MXY is nothing but this. Okay, and identity this map this is just duality map, because X tensor X dual, you can have a duality map from 1 to this is rigidity, right? The rigidity give you this map, and this composition, this OPE composition is also tautological, because you write it out and you do a duality map, right? Y dual tensor Y can map to the tensor unit, so it's gone. Now you got this one. So this is also very The other one is also, well, this tell you the tensor product structure, okay? As a consequence, okay, well, it turned out that we obtain an enriched category, okay? This enriched category, I'm using this data to describe this enriched category. It turned out that this construction can be generalized in a much more general context. So this is called a canonical construction of enriched category. More precisely, so perhaps I will skip a lot of detail because it's too long. There is a canonical construction of B enriched monoidal category. I didn't know this. What is B? B is a braided one. B is a braided, M is monoidal. Satisfy certain properties. Okay, basically the property says that M is a B module. But M is not only a B module, M is also monoidal. So this condition is a little subtle. This condition is a little subtle. So the B have to map to the dream field center, but that's too technical. I only want to tell you that the B acts on M. M is a B module, but with a somewhat enhanced commutativity because B is braided and M is monoidal. No matter what, okay. As long as you have such a pair, B acts on M, you can do the following construction. You can construct the enriched category by assigning the Hom space as the internal Hom in B. Given a pair of X, Y, in M, you can always have an internal Hom in B. B bar is that's the anti-braiding part. We can ignore it, okay? And using this construction, everything else is standard. Everything else standard. Okay, then you got a enriched category. Because B is braided, M is monoidal. These categories turn out to be also monoidal. So I will ignore the detail. Okay, if B is only monoidal, M is ordinary category. You got an enriched category. Because M is enhanced to a monoidal one and B is enhanced to a braided one, they all together they become a monoidal. Okay, the enriched category also have monoidal structure. Okay, so this is a more general construction of this one. So this is just special case of the more general construction. So let me, so this canonical age is turned out to be obtained from the pair of this one. Remember that given such pair, we can have an enriched category, right? Now, if you give this pair, if you give it the C and the C enriched in C self, multi-tensor category C simply give a enriched category C enriched in itself. Okay, so I would denote this C enriched in itself as this notation. So this is more easy to see what it is. So the canonical construction. So this canonical age is nothing but this one. V is what we told you before, and C enriched itself. Okay, so I also these for the time reason, maybe I'll just skip this one. But the question is, remember what's our motivation? We want to find a solution to this equation. So we want to know, now you construct something which describes the observable on the gapless boundary. Does it satisfy this equation? Does it provide a solution to this equation? Okay. This comes from the nature, right? We don't know. Okay, but I have to, before I present the answer, I have to tell you that now you have to define the notion of center carefully, because this is the enriched category now. Oh yes, you can do it. I won't go through the detail. There is a notion of center for enriched category. Okay, this is too complicated, but what I want to give a remark. These notions satisfy the same universal property of notional center, but in a new two category of enriched category, where an enriched functor is allowed to change the base category. So this is a much more complicated two category of enriched category, much more than the standard one. So the notion of enriched functor was changed. You are allowed more wild enriched functor in order to make sense of this notion of center. Okay, but anyway, there is a notion of center, which is standard one, and the punchline is yes, it provides solution. Okay, so the physics tell you how to solve a mathematical equations, and moreover, my collaborator Zheng Hao has shown that this enriched monoidal category is actually a fully dualizable object, which gives a fully extended TQFT. Okay, that's our original motivation, right? Whether a rest-seeking integral FT can be extended to a point.
Okay. So basically, this problem you have solved the completely, right?
Yeah. So that's one solution. We want to find more solution, right? So that's very easy to find more solution. The more solution can be obtained in this way. Consider so general chiral gapless boundary can be obtained from something called the topological recrotation, which is defined by a gap domain wall between two faces. Consider C is a multi-tensor category that define a topological order, and BC is another topological order, and you consider a gap domain wall between them, and we know what the mathematical description of this configuration. This configuration simply tell you that there is a braided equivalence from B bar, that's anti-braiding of B, box the link tensor product with C, and equipped with braided equivalence to the dream field center of M. That's the definition of gap domain wall. Okay, mathematically, given the fusion category, such that its dream field center is equipped braided equivalence from this to this. That's the mathematical definition of domain wall. But once you have that, you can do something quite miracle. You can just fold it. You can pair B and M. You pair B with M and produce an enriched category. And you find the V such that mod V equal B. Then you produce a solution to this equation. And we show that this is all the solutions you can get. Okay, this is all the solution you can get, and you can. So that means the boundary block duality holds for all these gapless boundary as we predicted. So let me present this fundamental result. Let me summarize what we have done. Okay, what we have done is this. Let me look at the time. Am I okay? I still have some. Okay, some time. Okay, so let me summarize. Okay. It turned out that we're looking for a gapless boundary, but our classification theorem automatically include the gapped one. So let me also say gapped. Okay, gap and the gapless boundary of a 2+1D topological order described by a pair CC, and where C is a unitary multi-tensor category and the small c is a chiral central charge, are classified and described by a pair. Okay, a V and an enriched category. The V is called, or sometimes we call it local quantum symmetry. It's a unitary rational VOA of central charge C for chiral gapless H. So a chiral gapless boundary. So if the boundary is chiral, then it's a VOA. What if the boundary is not chiral? It's possible. Okay, it is a unitary rational full field algebra for a non-chiral gapless boundary. The full field algebra is just it is chiral combined with non-chiral part. It's a generalization of VOA, a notion which was introduced by Ija and I in 2007. Okay, it's a non-chiral generalization of VOA. Okay, and in particular, when V is trivial, it's still okay, right? V equals C is a trivial VOA with a central charge 0. Then this case is exactly gapped boundary. So gapped and gapless boundary all unified in the same mathematical framework. Okay, what's the second part? Second part is the enriched category. Okay, it is a, well, this is a little technical. M is a fusion category equipped with a braided equivalence. We have seen this. And these are enriched category obtained from this phi. Well, remember this phi. Using this phi, you can do a canonical construction of the enriched category. You obtain this one. We give it a name called topological skeleton, but we don't use it much in this talk. But in particular, because it's a canonical construction, all the harm in the internal in the enriched category is given by the internal harm. All the internal harm is the object in the model V. Okay, so that's a fundamental result we obtained today. Okay, we got a classification of entire gapless and gapped boundary of 2D topological order. Okay.
So
and moreover, yes.
Oh, I'm just saying that the here the gapless. So basically, you are saying that the gapless means that you have this rational VOA.
Right.
But rational VLA, why it's continuous? The spectrum is continuous.
Oh, why is continuous spectrum is well, for mathematician they always grade it, right? But for physicists, this grading is depending on the size of the system. When the size goes to infinity, they will at the limit that they're approaching zero. Yeah. So
okay, so it's the in the limits.
yeah, in that
okay,
limit. Yeah.
I see. Okay.
Yeah. Okay. So oh, by the way, so oh yeah. Anyway, so let me. It turned out that once we have the gapless and the gap unified theory, we still have the same boundary Bloch relation. We have the center of the enriched category give the Bloch unitary multiplicative category. So you can have a different boundaries, and each different boundary are described by a different enriched category. Okay, but their Bloch is the same. All right, actually, it turned out that they share, so different boundaries share the same Bloch as their Dunfield center if they are Morelli equivalent, even only if they're Morelli equivalent. So the same thing happened for gapped one, and the same thing happened for 1 + 1 DCFT. They all have the same thing. Okay. And as a consequence, we can propose a more complete boundary Bloch relation. We can consider different boundary, even have a different Bloch. Okay, so different boundary can have a domain wall, and this domain wall also have a relative 1D Bloch. Okay, so that's a more general one. You can show that this define a well-defined functor. Not only is a well-defined functor, it's actually not, it's a faithful. You can, if you choose the target category properly, it becomes a monoidal equivalence. Okay, so this is generalized boundary Bloch relations. It's a precise mathematical theorem. It's a mathematical theorem. Okay, generalized quite many standard mathematical results in the fusion category. All right, in the remaining time, let me see what do I have a few minutes? Okay, maybe a few minutes, 3 minutes, or okay, a few minutes. In the remaining few minutes, I want to show you how to use this enriched category to compute a process of dimension reduction such that it automatically generate all the boundary open-closed CFT, a rational CFT we know. Okay, before I do that, let me tell you how to do this. What is the dimension reduction? I want to tell you how to fuse to gapless domain wall. Because gapless boundary and the gapless domain wall are essentially a similar thing. Once we have the gapless boundary theory, we also obtain a gapless domain wall theory. Okay, that's the same thing. Always give a pair where U is a chiral symmetry or non-chiral symmetry on the domain wall, and another one is enriched category. Okay, they always look like this. Now, how you fuse this two? Once you give two such domain wall, can you fuse them? Yes, you can fuse just pairwisely. U is fused with along the topological order. Okay, U is fused with V, just like a VOA tensor product over C. Okay, two VOAs tensor product over C. Okay, what about the enriched part? That's very easy. Look, superscript fused with superscript. Okay, the underlying one fused with underlying one, but remember the underlying one is fused along the topological order. The D is another multi-tensor category. So these have to be done a relative tensor product relative to a multi-tensor category. Okay, this can be done. Okay, all right. So I'm just telling you that you can fuse two domain wall. Okay. Next, I wanted to show you this. I won't show the detail. I just wanted to show you that the same physical configuration. If you change the coordinate, if you change the complex coordinate on the worksheet, because this is a worksheet, you change the complex coordinate to the complex conjugate one, you can obtain exactly physical equivalent description, physically same physical configuration, but different mathematical description. So that means you change the chirality, but the physics is the same. You just change the coordinates. Okay, and you can get the anti version of the description. Okay, look at the orientation is changed. Once we change the coordinate, the orientation is changed. Okay, local orientation is changed. Okay, now I want to do something miracle. Okay, remember that we have a gapless edge of 2D topological order. Forget the blue line, the green line. Forget the green line. Forget the green line first. Okay, green line is a domain wall, but if we forget it, just a block, and with a gap domain wall, but with a gapless boundary. Now I used the trick in the previous slides. The same configuration allow me to do a changing chirality. Okay, remember that everything is moving this way. The chirality tell you left moving or right moving. But now I artificially change the previous one is moving this way. Now I artificially change it. Then I have to change the VOA to the anti-VOA, anti-chiral, anti-holomorphic part. Okay, if I do that, I'm allowed to change the orientation. This is shown from the previous slide. The physics is the same. Okay, I change the orientation, but I change the chirality at the same time. That means I didn't change anything. Once they have a compatible orientation, I can fuse them. I can fuse along this green line. Imagine there's a green line. Then I squeeze the cylinder. I squeeze cylinder to a plane. Now I got this plane. When I squeeze it, when I squeeze it, it's the same as fusing this two domain wall. Okay. So I fuse this. I got that. Remember, I'm gonna using this fusion formula. The fusion formula is given here. I explain it. Okay. Now we use the same formula. You just compute it. Okay. You compute. You got this one. Now you got a. So that after you squeeze it, you got worksheet, and this worksheet contain chiral part and anti-chiral part, and enriched in this is dream field center of C. M is enriched in dream field center of B. Okay, this is a new enriched category. What this enriched category tell you? Using the enriched category, you can immediately tell you that the chirals, in this case non-chiral. The non-chiral fields leaving on the entire worksheet is given by the internal harm of the trivial the tensor unit of M. Okay, you can compute it. Once you compute it, you see immediately that this is nothing but a modular invariant box CFT living in the double of C. And this modular invariant box CFT also gives the so-called Lagrangian algebra, which appeared before. In particular, for example, M just equals C. M equals C just means that there's no domain wall. Just you can forget about domain wall. Just everything inside just C. There's no domain wall. And this one is what? It's precisely the modular invariant, so-called charge conjugate modular invariant box CFT, closed CFT. If M is not C, you simply obtain a different modular invariant of box CFT. So in this way, you recover all modular invariant CFT, closed CFT.
So basically, when M is not equal to C, you get this non-diagonal one, right?
Yes. Yes.
Okay.
Yeah. Okay, I'm quite almost finishing. So in this picture, not only you can permute, you can get the bulk. You can also consider a non-trivial boundary. You can also consider a non-trivial boundary on the gapless edge. I won't give you the detail. You also get an enriched category. And after you do the squeezing, you also get this one that become boundary CFT. So in this way, it turned out that all the internal harm inside this enriched category are precisely boundary CFT that compatible with the bulk. So all this CFT here, this red line, blue line, are all automatically CFT, boundary CFT compatible with same bulk. And now we have a mathematical way to cover those. How to do those? This MM is precisely just a module over the bulk. In the bulk, you have a enriched category. And on the boundary, you also have an enriched category. And the bulk enriched category acts on the boundary enriched category. So you just get a representation theory. And later on, we can just use representation theory to classify all the boundary CFTs. Okay. All right, I'm almost done. So let me summarize. I have found a mathematical description and a classification of gapless and gapped edges of 2D topological order. And all the rational boundary box CFT can be naturally recovered from this varied dimensional reduction. And this theory opened the way to study topological phase transition and the gapless quantum liquid phase in all dimensions. I don't, yeah. Why is it work for all dimensions? This is something interesting, but I don't have time to talk about it. But mathematically, it also opened way to study enriched monoidal category. Why is that? Because look at this, the enriched category and their representation have a different base category. So this enlarged older enriched category theory. So you have to change the base category all the time in order to have a very rich representation theory. Otherwise, you get a very uninteresting one. That was the people find in 80s, which is not so interesting. I think now the enriched category enter a new phase. Okay, thank you.
So thank you. So Lisa, you can stop the recording now.